Okay, so good afternoon, everyone. Thank you. I would like to start my presentation with one of my favorite photos from my research, showing 25 wave energy converters in a wave basin of DHI. This is a photo of the consortium of the WECwakes project, coordinated by Peter Troch from Ghent University. Other partners are Jens Peter Kofut, Aurélien Babary, Michel Benoit, Tim Stallard, David Foran, Matt Foley, and Jens Kierkegaard was the local manager of our project. So this is a short overview of my presentation. I will start with an introduction and problem statement. I will talk about the research objectives and the methodology we have followed. I will give some main experiment results and deliverables, and I will sum up some conclusions. Wave energy converters, abbreviated as WECs, are devices that capture energy from waves and convert it into electricity. There are a lot of different concepts, but mainly two types of devices. Those based on the oscillating principle, like the Pelamis, and those based on the overtopping principle, like the wave dragon. But what they all have in common is that they have to be installed in large numbers, forming large farms or arrays, and covering large surface areas in order to produce sufficient power. But these large WEC arrays have problems with WEC array effects, which are distinguished in intra-array interactions and extra-array effects. Intra-array interactions occur between the devices within an array, which means that power production of the entire array may be smaller or larger than expected. In this panel, you can observe intra-array interactions. These green circles symbolize the plan view of 3 point absorber devices. Incident waves cause the response of these devices, thereby creating diffracted and radiated waveforms. And these combined waves affect additionally the neighboring devices. And these are the intra-array interactions influenced by the WEC array layout, the spacing and the number of the devices, and of course the wave conditions. We also have extra-array effects, which are mainly expressed by wave height attenuation due to wave energy extraction. In this panel, you can observe extra-array effect predicted using our wave propagation model, MOUTWAVE, developed at Ghent University. These are contour plots of disturbance coefficients for waves propagating through different arrays of devices. In the left panel, you see you observe wave energy extraction from the incoming waves by a row of 3 devices, while in the lee of the 3 WECs, a zone of wave height attenuation is visible. Now, when the distance between the devices becomes larger, also this zone becomes much different. And again, when we go from 3 to 9 devices, this zone is different. These extra array effects are very important because they may influence other activities in the sea, coastal ecosystems, coastline morphology, or even the coastal defense conditions and parameters. So these WEC arrays may have significant environmental impact, which may be positive, like offering a sheltering effect, or negative. So it's important to be able to predict those WEC array effects in order to determine the optimal array geometrical layout in terms of wave power absorption, and in order to find a balance between environmental impact and wave energy advantages. Nowadays, WEC array effects are theoretically and numerically treated in detail. However, since recently there was a lack of experiments with large WEC arrays, which hindered validation of numerical models, and this was one of the missing links for significant progress in the wave energy sector. So due to this, there was a huge necessity for experiments with large WEC arrays, which have been realized within the program HYDRALAB and within our project WECwakes in the shallow water wave basin of DHI. Objectives of these experiments were to get a better insight of both the intra-array interactions and the extra-array effects and their effect on wave power absorption by changing the spacing, the number, and the geometrical layout of the devices in an array. Also to compare data with results from the point absorber theory, and of course to provide experimental data for validation of a wide range of numerical models like phase resolving models such as mild wave, phase averaging models such as Swan, and BM solvers such as WAMIT. Especially for this array testing, a WEC has been developed. It does not suggest a new WEC concept. It has been made appropriate for accurate numerical treatment, and it is robust and simple to use in a basin. So in the right panel, you see the developed WEC with its parts. It has a WEC shaft and a gravity base, which are the support system of the WEC. It has a WEC buoy, which is the only moving part of the device, and it also has a power takeoff system or PTO system, which is the part of the device where power is extracted from the incoming waves. It's a point absorber WEC with a simple generic geometry, and it can only heave. It has low-cost construction so that it can be reproduced in large numbers for array testing. It is easy to reposition it within an array so that we can test a lot of different array configurations. And it has measurable buoy response and energy extraction so that we can easily compare results from one geometrical array configuration to another. This WEC has been constructed in the workshop of Ghent University and has been tested thoroughly prior to the WECwakes experiments in DHR, in the wave flume of Ghent University, in the wave basin of Queen's University Belfast, and in the large wave flume of Flanders Hydraulics Research. So 25 identical copies of this developed WEC have been used in the shallow water wave basin of DHI, and these are pioneering experiments and worldwide unique. So this is a photo of the 25 devices in aligned configuration. On this photo you can also observe the support frame which we use to test a lot of the different array configurations, and also some of the wave gauges. 3 types of measurements have been taken during the test simultaneously. Time series of the horizontal wave-induced surge force on the WECs, the vertical displacement of the buoy by using potentiometers, and surface elevation by using a network of 41 resistive wave gauges. And all these data are time series. Here's a short overview of the database. We performed almost 600 tests, focusing on different wave types and angles of incidence, and with these ranges of wave period and wave height. This database is unique, and we started with by testing an individual device, then a column and a row of 2 and 5 devices, 2 columns of 10 WECs, 13 WECs in a staggered configuration, 9 WECs in aligned configuration with a spacing 5D and 10D, where D is the diameter of the device, and reaching up to 25 devices in aligned and staggered configuration by shifting those 2 rows. Here are some photos during the experiments. At the top left panel, you see that only 2 devices are activated, while all the rest are held above water surface. This was an easy way to test a lot of different array configurations. At the top right panel, you see the WEC models under oblique wave attack. At the bottom left panel, you see tests with a staggered array of 13 devices. And at the bottom right panel, you see tests with a column of 5 WECs. Some first analysis of the data have provided results for the effect of intra-array interactions on the overall power absorption of the arrays. Here I will present results for the large arrays, 25 devices, for long-crested irregular waves. So the Q interaction factor has been calculated, which is defined as the ratio between the power absorbed by the array to the theoretical power absorbed by the array, as if there were no interactions between the devices. When Q is larger than 1, then we have the power absorbed by the array is larger than that absorbed by 25 isolated devices, and in this case the intra-array interactions are positive or constructive, and when Q is smaller than 1, the intra-array interactions are destructive. So for the aligned array of 25 devices, this Q is 1.03, which means that the intra-array interactions in this case are slightly constructive by 3%. I would like to mention that this small percentage does not mean that there are almost no intra-array interactions. It actually means that positive interactions compensate the negative interactions. And we know that there are interactions because none of the WECs of the array has power output equal to that to the power absorbed by an isolated device. Now, when we go to the staggered array, the expectation is that we have higher interaction factor, which is confirmed by a value of 1.16, which means that in this case, the intra-array interactions are highly constructive by 16%. Also, a first data analysis has provided results for extra-array effects, whereas the impact of the WEC farms on the wave field, which is expressed by wave height attenuation. Again, I will show results for the 2 large arrays. This contour plot at the left panel presents results for wave height reduction. The crosses indicate the location of the wave gauges, while the rest of the symbols show the location of the 25 devices. So we see that in the Lie of 25 aligned devices, we have up to 18.1% wave height attenuation, while when we look at the same location for the staggered array, this attenuation reaches almost 21%, which is normal because in this case we had higher power absorption by this array. And let's take a look at 2 videos from the experiment showing the response of the devices. So you see that we have tests with irregular and regular waves, and the response of the devices is not identical for all of them, and this shows that there are intra-array interactions. Again, you see that the WECs do not have the same response due to these intra-array interactions. This is a close-up. And the second one, showing more regular waves, but still the response is not identical for all 25 of them. Okay. A full video is available on the website of DHI. And this is a short overview of the main research deliverables and conclusions. An extensive and unique database has been created, almost 600 tests, This database includes WEC response, wave-induced forces, wave field modifications. There are results for WEC farm power output. This database has a large parameter variation and is useful for numerical model validations. A first database analysis shows that there is a significant effect of intra-array interactions and extra-array effects on both power production and wave field modifications. And based on this data analysis and on literature study, a first series of guidelines for design of the geometrical layout of WEC arrays have been derived in order to optimize power absorption of the arrays and to limit their environmental impact. Also, in terms of dissemination of the WECwakes results, now we are 1 year and 4 months after the completion of the test. We have already several international conference papers. The last one was in ICC a couple of weeks ago in Seoul, and the next one will be COAST-LAB 14 in Varna, Bulgaria. We also have published in Energies journal paper, and we have 2 journal papers in coastal engineering and renewable energy under review. This data have supported PhDs, my PhD, and 2 new PhDs from students from EDF and the University of Edinburgh. And these data are used by a large number of researchers from all WECwakes partners. Also, finally, there is a high interest in the database by researchers outside from our consortium. And these researchers are not always related to wave energy. They are also modelers of wave structure interaction. There is also more analysis underway, and this was my presentation. Thank you.
Thank you, Vicky. And we have time for a couple of questions. And Peter? Ole. It's late. It's late.
In the layout with the staggered, where you got 16% improvement, had that been optimized?
No.
Layout, because presumably it will change as you change the distances between individuals.
Yes, this is a result only from one wavelength.
Yeah.
This has not optimized. There is still a lot to analyze and to look into. It's a huge database, but
so there's a possibility of get 30% more.
Actually, there is also from the side of the wave energy devices, it can be optimized because these devices were not optimally tuned for these wave conditions. So there is definitely space for optimization.
If I may ask another one related to operation of such a wave energy field, what do you do about when you get a really big storm? Do you leave them out there and do you hope to find them again? Or?
Well, I'm not the person to give an answer to this question because I'm looking at the wave field only. I'm not a wave energy developer. Yeah. But there are a lot of concepts, several concepts, where they have thought about this situation. Some of them they taken out, like the Waystar in Denmark. And I hope the wave energy developers take into account this option or this situation when they design.
The reason for my question is actually that if you take them out when you have the big waves, that means that the storm waves will attack the coast and erode the coast, and then you pick up most or hopefully most of the energy when you have more gentle wave conditions, which means you're not going to rebuild the coast. So there's going to be an environmental problem there.
Yeah.
No birds are getting killed. But,
thank you, Ole, for your
entirely
questions.
John.
Another question Down.
Yeah, actually, I have two short questions. So, for first question, you might have said that, but I missed it. What is the efficiency of that wave energy extractor?
Well, this you mean this wave energy device?
Yeah.
For the wave conditions that I have presented, this wave energy device has been optimized in regular waves, so it has the optimal, the maximum efficiency. Now, it's not really an topic of this research, the efficiency. We only wanted to get measurable wave energy extraction.
Yeah.
So.
I was just curious. I mean,
yeah.
It's order of 5%, 10%. I mean, does anyone know the answer? Well, and second question is, so you were considering all regular grid, so
only
arrays. Regular. Yeah. What happens if you put a kind of random distribution? I mean, any idea?
So these are the arrays we considered. Yes. This is a question, is it a theoretical question of, because we haven't tested it. I guess it's something you can also test by doing numerical modeling. We tested the most usual array configurations. Of course, we didn't have time to test everything.
Thank you very much. I think this was the last question we could find time for now. I have a few announcements before we go. Thank you to I have just 2, 3 announcements. First one, there will be a visit to the LENIAC installations tomorrow.